Now what do you mean by that? Diffraction of light. So the diffraction is nothing but a bending of light. Yeah, so in short, it is nothing but a bending of light, and since there is a bending of light will occur, so this is the source of light which is going to emit the light. So there is, you can say that, yeah, so here I just gave, so this is the only portion through which the light will pass through it. Yeah, so here you will get the geometrical shadow and this part will get illuminated. Yeah, so this part you can say that it is illuminated, but at the same time you can say that, so this portion is having the geometrical shadow, the light can't reach over here. So we can say that the light is getting spread. The light is getting spread when it is passes through that small aperture AB. Similarly, this is the obstacle which I kept over here. So obviously the light will just passes from this side. Yeah, and this one is the geometrical shadow and this one is now illuminated region. Yeah, so you can say that the light gets bent when it just passes through that small aperture or through that small slit. Yeah, and definitely it is getting bent around that edges, yeah, or around that corner. So that effect we are going to call it as a diffraction of light. So that when the light, just take one piece of cloth and take it towards the light. Yeah, so when the light passes through that piece of cloth, the light is getting dispersed. Yeah, so you can say that the diffraction, the bending of light comes or occurs when it just passes through those pores or through those holes of those clothes. Yeah, and it gets spread, on entirely on that cloth. So that is what I can say that. So that is a diffraction. Again you can say that, so the ring, so you can say that when the sunlight passes through those your clouds also, so there is a kind of ring or different colors formation around that edge of that cloud. So that is also, you can say that, which is nothing but a kind of, that is a diffraction. So that is a bending of light. So this is what we can say for this diffraction. So the same thing with the help of, you can say that with the help of that water effect, water analogy. Let's say this is water which is coming and then suddenly if I block it, so likewise these waves are getting bent. Yeah, so you can say that, so for this particular case, so it will get bent. Yeah, so the same thing, instead of water it is nothing but the light. Yeah, so now it getting bent in this way when it came out of that your aperture or through that hole. So that diffraction, we can say that two kinds of diffraction, one is the Fresnel and another is a Fraunhofer diffraction. Again, this source and screen are placed at a large distance from the aperture. So you can just use that convex lens to just merge that at a particular point. So this is what we can say for this diffraction at a single slit. So what we are going to do over here, so this is a source, yeah, so which is, you can say, again which is passing through that your slit. Then again obviously the different part of the slit, they are going to emit the rays. So there are different, you can say, the formation of your dark and bright band occurs over here also. So you have to find the condition for the same thing. Yeah, so this is what we can say over here at point O. Let's say obviously you can say all the rays are going to converge, so there is a maximum intensity at point O. Now what about the point P? Yeah, so if I consider that point P, then you can see that what is the path difference. So this is the extra distance that has been traveled by the light which has been emitted from the point B. So this path difference, and this slit width is A. So this path difference, simply I can write it down over here, which is nothing but A sine theta. So for this particular case, now again how we are just going to look at this. So this is what we can say, that is your A sine theta. So now this part difference, one under what condition, it is nothing but your constructive interference, and that is what your destructive interference. So let's say for constructive interference, yeah, and for the destructive also, that we will just discuss. Yeah, so for constructive and for your destructive, or either you can say that, so that is for your, let's say the first one, the formation of your dark band, the formation of your dark band. Now the condition is that, so this A sine theta is equals to n lambda, that is the condition for your dark band. So let's say for n is equals to 1, so you will get A sine theta is equals to your lambda. So now what we are going to do over here, we are just going to divide this slit into two parts, so that is a A, C and B. Yeah, so again what we can say over here, so when the light is going to reach at point P over here, obviously So when they reach at point P, so at point P I can just show it. Yeah, so this is A, then this is your C, yeah, and again this is B. Yeah, so when the waves which has been emitted from this A and B and C, when they reaches at point P, you can see that there is a phase shift between this A and C, which is your again that is a 180 degree, that is a pi, and between this C and B also that is a 180 degree. So the phase shift between these two extreme point is nothing but lambda, that is a 2 pi. Yeah, so we will divide this slit into two parts. So that is, let's say one is AC and another is CB. So for every point, so that is for each light which has been emitted from that your part AC, yeah, there is exactly, you will say that there is a destructive interference produced by one of the source from this part CB. So there is a destructive interference when they reach at point P. Yeah, so that's why we can say that, so there is a destructive interference will occur, yeah, and you will get the dark band. So the path difference between these two extreme end is obviously which is lambda. So for A to C, the path difference is lambda by 2, and for C to B, there is a path difference of lambda by 2. So the path difference between these two extreme ends, that is a lambda, and that is the condition for your destructive interference. So this is what we have seen, the path difference which is A sine theta, yeah, and for the condition of your dark band, that should be equals to n lambda. So likewise corresponding to that, it might be, so that is a first dark band. So this is the condition, so that we have seen, that is for your first dark band. So again for n is equals to 2, definitely that is for n is equals to 2, we will just divide the slit. So here likewise we divide the slit into two parts, yeah, so first and second. Again for n is equals to 2, we will divide the slit into 4 parts, yeah. So again similarly, so definitely you can say that you will produce the dark band over here. So one more thing, yeah, so now this is how the distribution curve for that your diffraction pattern which will get produced, yeah. So one more thing, so now what is for the bright band, so what is the condition for your bright band, so that also we will see. So for bright band, the path difference which we have seen, that is nothing but A sine theta, and it has to be equals to 2n plus 1 lambda by 2. Okay, so for this condition again we can say that we will just divide this slit actually now into 3 parts, that is a 1, yeah, let's say this is 1, this is 2, and this is 3, yeah. And when the light from this different part will reaches at point P, what is going to happen exactly? So there is a destructive interference from the first and second. So the intensity of light when it reaches at point P, it gets cancelled. But again still there is a light which is coming from the third part, although its intensity is only 1/3 of that total. So still you will get the bright band, but obviously which is of less intensity. So this, if I put n is equals to 1, obviously this you will get, that is a condition for that. So that is nothing but 3 lambda by 2, yeah. So that is a first bright band. Again for the second bright band, so that is a 5 lambda by 2, yeah. So again you can say that, so definitely according to that you will find the condition for your bright band also, yeah. So this is how we can say about this your dark band and bright band. So one more thing that we can just calculate for this particular case also. So this sine theta also you can write it down over here. So this is nothing but your y upon d, yeah, and this part difference also, so which we have calculated over here. So let's say A sine theta, yeah, so A sine theta is equals to, that is nothing but lambda. So sine theta is equals to lambda upon A. So this is yd upon d is equals to lambda upon A. Fine. So according to that you can find, so this is nothing but y is equals to lambda d upon A. So this is the distance also which you can calculate. So that is the distance y in terms of that slit width, also you can find it out. So again the distribution curve, you can observe it carefully. At the center only you will get the bright band, but as you move away you will get the intensity distribution curve. That intensity gets changes, the amplitude is also getting reduced, because obviously we just said that. So for the bright band, only first bright band, only 1/3 of portion is responsible, for second 1/5, likewise it goes on reducing. Yeah, so now what is the main difference then between that diffraction and interference? If you observe both that intensity graph, yeah, so the amplitude in case of your YDSC is same, but here the amplitude goes on decreasing continuously. Here we are just using only single slit, but in YDSC there are two slits. There is a interference between the different parts of that, you can say, your wave front, which has been emitted from the same slit. But in case of your YDSC, there is interference between the wave fronts which has been emitted by the two different sources. So these are the few things that just determines the difference between your diffraction and your interference.